be able to do all what I plan to do, but again, you have the notes, you can look at that. And it's the style of the notes is a bit the same than the lectures. Rather than doing all the computation, I try to give the idea. And if you really want the computation, you can look at the papers. There are full references. Sometimes there are full computation, but it's just by chance. Okay, so let us see where we were yesterday. We got a random variable x, and we found the density with the formula. Yes, x, real random variable. Okay, that means that if integration by parts holds, we have a density, we have even an explicit expression of the density, and this is also continuous by bounded convergence theorem. If we even know something about this random variable, say for instance that this one, I call it f yesterday, and then I stick on f. X1 is in L2 of omega. This is a random variable, so it's a measurable function on the probability set. Then what we get is we use Cauchy-Schwarz inequality, for instance, and we get that this is the expectation of H1 X1 square half times the square root of the probability that x is larger than x. Okay, and you see that that means that this formula gives us the decay of p by means of the tails of the random variable. So that if the random variable has some good moments, that means that the density is decaying stronger. So now the problem is, how do we get the integration by parts formula? So there is no unique way to do this. We already saw this, because there is no uniqueness of the. We can have many different ways here. And the point is that Malemán calculus provides a way to find these ways. Now, giving a survey of Malemán calculus in an hour, it's not easy, but I will try. And the idea is that I don't really give full definitions, but I try to find out the idea. Okay, so remember, in the integration by parts formula was the expectation of phi prime of x is equal to expectation of phi of x times, for instance, h1 x1. We saw many different, but the idea is that here there is f prime, there is random variable, there is a derivative here. The derivative has disappeared, has to go somewhere. So when we do integration by parts, we move the derivative from some derivative in space in some variable to a derivative in space of the same kind of stuff. The idea of Malemán calculus is that you are moving a derivative from the space variable to the probability variable. So we are going to do derivative on the probability space. No, let me give an idea of this. So, which kind of functionals we will be able to differentiate? Okay, this is the main point. Let's start with the Brownian motion, and for simplicity, I restrict to interval 0, 1. This is not essential, but it makes my life easier. So we are going to derive function of this like functional of the path. Okay, so this is the kind of functional we are going to derive with Malemán calculus. Why? Well, for instance, if you are interested in SDE, this is a very good functional, because okay, this is the right time to to distinguish between what is a weak solution or martingale solution for an SDE and what is a strong solution for an SDE. There are several ways to define these, but I want to give an idea of this. Because for a weak solution, so like let's call it intermezzo, this is a weak solution. We define a weak solution, weak martingale solution for Navier-Stokes, but the underlying idea for martingale solution is the same. We look for a probability measure. And this probability measure has to be a solution of the problem. That means that there is a probability space and a random variable with the probability of the solution, and there is so the probability of motion or linear process, let's say whatever. So the linear process is part of the solution, such that the equation is satisfied. So in a weak solution, the linear process is part of the solution itself. So what is a strong solution? A strong solution is the one in which the data of the problem is the process itself. It's not its distribution, as we saw in the case of a weak solution. So I'm given a linear process, and I want to solve some equation with that given process as a driving noise. So in a way, this means that I'm given a linear process. I have some rules to manipulate this linear process, and as an outcome, I get the solution. So the solution of a strong solution, the strong solution, is a functional of the linear process, and this functional is the way I manipulate it to get the solution. So in a strong solution, we have the principle that we start with a driving, the driving noise. You can see it as the derivative of a linear process, and then we get the solution of this equation. So among all functionals that we can derive, the most interesting one, at least for our purposes, are exactly those that come from strong solution of SDE. Well, this is not the only example, but this is one of the most important examples. Okay, now we go back to the derivatives. So what we want to do in this way, so we want to do some kind of derivative of this functional has the derivative along the linear process. What does it mean? Okay, a good way to understand this derivative is to do a derivative along the increments. Because let's go back to this interpretation in terms of a SDE. So we have our solution of the SDE, it goes like this. And then we want to do a derivative, right? So we have to make a perturbation. How the calculus of variation works, right? So we do a perturbation on the variable, and we get a perturbation in the function. So we do a perturbation on the noise, and then since we can look at the driving process as since this is a Gaussian process, as a sum of independent increments, this is this is infinitely divisible. So at each small interval, we perturb the noise, and we have a different solution, right? So that's why I want to see this as a derivative on the increments. Okay, let us give us a bit more precise definition. Okay, the scheme to show how to differentiate such functional is, well, first, we cannot differentiate any function, right? Derivative is not a property of any function. Some functions are differentiable and some other are not. And so it will happen that we will find that some of these functions are differentiable and some aren't. Okay, so which is the idea we use to define the derivative? We define the derivative on a set of simple functions, And then by approximation, we can differentiate any function which is limit of this simple function, as long as the operation that we have defined is stable along the limit. So it's a typical way to define mathematical concept. Okay, so we start by the simple functionals, and I chose the interval 0, 1 because, well, it's simple, and then I introduce the dyadic points. So for any integer n, t and k is k over 2 to the n, and k runs from 1 to 2 to the n. And dyadic points are nice because now I define this set, the set of simple functions is the set of those functions obtained as f of, now I say, n0 and 2 to the n minus 1, with f is C infinity with polynomial growth. Just to remember this is polynomial growth, I write this, but in R to 2 to the power n. Okay, where delta nk is the kth increment of the noise. Okay. So why the dyadic points? The dyadic points are nice because if you have them, you are just adding up, and so this means that this Sn plus 1 contains Sn, right? That's it. If I use k over n, these doesn't work. Right? This is not, so this is the only way, the only reason why we use dyadic points. Okay, so these are the so-called simple functional. Okay, so what is a simple functional? Is a function which depends on a number of increments of the linear process. Oh, obviously, the same set coincides with this other set, the set of functions which are function of sometimes. So Wtn1, Wtn2n, okay, is the same with f in the same class. Well, why this is true? Because each of these can be written in terms of increments. And for instance, Wtn2 is equal to Wtn2 minus Wtn1 plus Wtn1, okay? And so on. But so this is simply a telescopic sum. And so these two sets are the same. This one is easy, and this one by telescopic sum. And so this is not restrictive to do the derivative with respect to increments, rather than to do derivative with respect to single variables. The good thing about doing derivative with respect to increments is that we are dealing with a linear process, and increments are independent, while these random variables have correlations. Okay, so we are really sticking in the simplest setting. We differentiate with respect to independent random variable, and in our idea, if we are perturbing something and something else is independent, should not be affected by this perturbation. Okay, so that's why we like independence, and we do it at the sampling at the dyadic points because dyadic points are easy and they are very convenient. So okay, so from this point on, we stick on this simple function.
Sir?
Yep.
So are we fixing one Sn or taking the union of all Sns?
Sorry?
The set of simple functionals, will we fix it to be a single Sn or the union of Sn?
Oh yeah, sure. We are going to take a union. We are going to take the closure of the union, but one step after the other. I mean, because this is for those which depends on the first 2 to the n dyadic points, and then you increase n and you get more and more refinements, and then you take the closure, which is the union. I mean, and then you take the closure, but the closure with respect to which norm? This is what we need to understand. Okay. Actually, the main step, the major step here is, well, is to define the derivative, at least on simple functional, and to define then a norm on which we do the closure. And once we know this, so we define the set of functions which are Maillard differentiable as those which are limit of this simple function for this norm. Okay? So he already understood everything. So for all the others, that was fine. I mean, you were right. I mean, you got the point. Okay. For all the others, okay, so I keep going. So these Sn are increasing, and we define S infinity as the union of all Sn. Okay. Now I need another definition, and then we finally go give the definition of derivative. So we define simple processes. And I use Pn. And again, we can take we will do it for every n, and then we will consider P infinity as the process U to be the sum from k equal 0 to 2n minus 1 of some uk times the indicator function of tnk plus 1, tnk plus 1, and where each uk is a simple function. And again, Pn is contained in Pn plus 1, and we set P infinity as the union of all Pn. Okay. And now, define the Maillard derivative. So take a simple function f in Sn, that is for any n, and then the derivative prime s is equal to the sum from 0 to 2n minus 1. Let's see. We cannot start from scratch. We want to do a derivative, so we start from usual derivative, right? So here we have the simple function are simple function of the increments. So here we are dealing with a real function. We know how to differentiate this real function because this is C infinity in R to 2 to the power n, but still is a standard function. So we know how to do derivatives with respect to these functions. So this is the derivative of f, where if f is in Sn, f can be represented as f of dn0 dn 2 to the n minus 1. There is no unique representation for a functional. You know, since I'm dealing with dyadic, I take one of these increments, I split it in two with halving the interval, and I get a new representation, for instance, in Sn plus 1, and so on. So there is no unique representation. The derivative I'm going to write is invariant for the change of representation, right? I mean, otherwise we would be in trouble. So this is the derivative with respect to the kth integral, kth increment. So computed in the increment, and times the dk plus 1 computed in S. Okay, so let us see. We take a functional. This functional depends by a series of independent random variables. And these random variables are associated to some time intervals. So in any time interval, if I do a variation on the noise, only the corresponding increment will fill it, right? Because this is a process. Here? Because it's a process. It depends on time. Right? What do? Okay. I come back to the formula in a minute. Okay, so when we do a variation in the noise and we look at some interval, the only part, sorry, on the process, on the linear process, the only part, so the only increment that will feel that change in some interval will be the corresponding increment, because for all the others, they are independent. So it makes sense that we associate to this formula. Okay, let's see. We start with a simple function, and we end up with a simple process. I mean, that's why I introduced also simple processes. So we do a derivative of this one, and we compose these derivatives at different times. Because when we do the derivative with respect to some increment, that derivative will be felt only on that interval, right? And that's why we have a process. So we have an S here, and on the other side, there must be something which depends on S. And this is a process. Okay? You probably have a different definition, which is given in terms directly on the differentiable, the derivative, which is then can be seen as a process when you look at no problem. It's the same. Okay? So this is, so we have defined this derivative that goes from the simple processes to simple function to simple processes, and by considering the union, we can look at the derivative as going from S infinity to P infinity. So just never forget our aim. We want to move the derivative to a derivative along the driving process. So, or the underlying process which defines this process, this functional. So the way we are doing is to imagine we do a perturbation of the process, and this perturbation is felt independently in all the independent increments of the process. Okay, and that we get a derivative, which is a very natural definition. Once we know that these are independent, and these depend on some, so are based on some time interval. Okay. Now, as we learn in primary school, or we are mathematicians, we learn this in primary school. Once you have a derivative, you also have an integral, right? So let us define the integral in this case. So define the square root of the integral. Okay, if the derivative was going from the functional to a process, and then the integral is going to go from the process to a functional. Okay, so take a simple process. So we can imagine u is represented as uk times the indicator function tk plus 1, and define the square root of the integral as the sum from k equals 0 to n minus 1 of uk delta nk minus 1 over 2 to the n derivative of uk with respect to delta nk. Okay. And then the square root of the integral is also from Pn to Sn. You remember that for a simple process, the coefficients of the expansion are simple functional, so this is also, again, a simple functional. And also delta goes from P infinity to S infinity. Okay, a couple of remarks. The first is, just imagine here that this functional, which I define to be a functional of the process up to time 1, might be, for instance, actually depending only on the process up to time half. Okay, it might happen. I mean, it depends on the process up to time half. It's also depending on the process up to time 1. Simply, we are just adding something which is useless. So, but let us look what is going to happen here. That if this function depends only on a previous time, say a half, so here we will never see increments depending on the future of a half. And so for any s larger than a half, here we will get 0, because this derivative will be 0. It might satisfy you a bit, right? So if f is measurable up to time a half, then for s larger than a half, this derivative is 0. Well, it is extremely reasonable, because we are saying that we are going to do the variation on the Wiener process. But if you are only variating the process after time a half, our functional, which is measurable up to time a half, will be not affected. And so the derivative will be 0. So, right? I hope this will make you more comfortable. Yeah, okay. Okay, so second remark on the score of the integral, which is very, not really, doesn't look like an integral, to be honest. Unless we do a bit of consideration. The first consideration is that at least in some special case, we know that this is an integral. And the second is we are going to see that this is in a way, is the dual of the derivative. And that's why it deserves the name of integral. So first consideration, so first remark. So assume, yeah, essentially. Okay, the first remark is if U is a simple process and is adapted, adapted means that at any time the history of the process is synchronized with the history of the process. Let's see, I use the same one. The history of the simple process is synchronized with the history of the original Wiener process. So we cannot use this simple adapted process to forecast the future. Okay. So, but if this is adapted, we look at this, and so UK refers to the interval from tk plus 1. And so it cannot depend on the future of this interval. And so this derivative is always 0. And so the score of the integral is simply this. UK, and now I want to write explicitly what is this guy. This is simply WTNK plus 1 minus WTNK. So you see? And then there should be the other part, but this UK, in a way, does not depend on this one, because this is measurable with respect to what we know up to time TNK, and this is independent on what happened up to time TNK, because this is the increment in the future. So these two are independent. And if they are independent, the UK cannot depend on this. And so what we get is simply this, which is simply the integral from 0 to 1 of U dw. So it's an Eaton integral. Okay, so if we have a simple process, and we consider that we compute the score of the integral, and the simple process is adapted, we are simply getting something that we already knew. Hopefully, that is the Ito integral. Why, in general, we don't get the Ito integral? Why we cannot do a calculus for Ito integral? Well, actually, it can be possible, but some other directions. Well, the point is that when we do a Maillard derivative, we are simply doing it on the whole time interval, from 0 to 1. So there is no progression in the future. So the Maillard derivative itself does not respect adaptness. And so there's no reason why then its dual operation should do it. Okay? So that in principle we cannot use we do. The piece here is the Ito integral, but not in general. Okay? So I say again, if you look at the Maillard derivative, this Maillard derivative spans the whole time interval. Okay? But if we look at the Ito integral, in a way, if we are integrating an adapted process, is respecting the flow of time, while the Maillard derivative goes directly from 0 to 1. And then the score of the integral cannot do anything different. Okay, and the second remark is duality holds. That is, we have a formula that says that the expectation of a process, or simple process U times a derivative of f. Okay, let us see. A simple process U is done in this way, and since this each simple process is C infinity with polynomial growth at most, and these are Gaussian random variable. This means that each simple functional is in L2 of omega, because Gaussian can integrate polynomials, right? So if we want to integrate the square of this is the square of this, and these are multivariate Gaussian, and so this is polynomial growth, and we integrate against the Gaussian density, the usual heat kernel, the way you like to call it, and which is of exponential decay, and so we can integrate every of these simple functions, as much as we can integrate, in a way, in omega, we can integrate the simple processes. Okay, so simple processes, simple functional, are in L2 of omega. So I take a simple functional, I take a simple process, I do the derivative. So this is a process, this is a process. I can do the product in L2, 0, 1, which is the basis of probably what you see as a definition of, okay. Now you feel more and more comfortable, I hope. Yeah, fine. And so this is a product between two processes in L2, 0, 1, between U, a simple process, and a Malavant derivative of a simple functional. We take expectation. This expectation is finite because they are both in L2 of omega, and this is equal to the expectation of f times the integral, the square root of the integral of U. Okay, that's fine because it tells us that derivative and integral are dual, at least in L2 of 0, 1, which is, since on this side, there are both processes, so the product we can do is, for instance, the product in L2, and here they are functional, so we can do the standard product. So we can, in a way, invert it. And this is the basis to pass to the limit, because then what we will not show actually, but what the idea is that from these, you get that the Malavant derivative is a closable operator. Okay? And once you have this, you can just define it on his domain and so on. What's the time? Just to realize if we want to prove this property. Yeah, I want to prove it because I want to let you see why we have this term. Okay, so I will say partially prove it, because one part is an exercise that I gave to you, well, a bit more elaborated part of the exercise that I gave to you. I didn't check if you did the exercise. Maybe later. Maybe not. Don't worry. But the main point is I want to let you see another reason why these terms appear. Okay, the reason why this term might appear, we gave a heuristic explanation because we have no adaptness. We know that there is some future involved, but this does not tell us why the term should be this one. Okay, we understand that there might be something which correct the Ito, but there's no reason why it should be this term. And now I want to show you that why we have this term. And essentially, and now I tell you that the reason is we are doing the integration by parts after all, right? And in this finite setting, because these functional are not functional on the infinite dimensional process, but only on a finite dimensional sampling of the process. Okay? So when we do integration by parts here, we're doing integration by parts by means of Gaussian random variables. And so in the integration by parts, when we do integration by parts, not against the Lebesgue measure, but against the Gaussian kernel, the integration by parts is a bit more complicated. And there is an additional term showing up. And now you are guessing it. This is the additional term showing up. Okay, let us see. the process, the properties I want to see. So let's say that G is Gaussian, okay, with values in RD for some D. So this is a remark that we are going to use, and I need another piece of chalk. So this is G Gaussian, so it's G in RD, and I have two smooth functions, doesn't matter. It holds with less regularity, but smooth is safe. And then the property is the expectation of the derivative of f with respect to some xi computed in G times G of G is equal to the expectation of f of G times G of G, the ith component of G. G is it's a vector times sigma I square, and I tell you what is sigma I, but it's the variance of Gi minus the derivative of G xi G, where sigma I square is equal to the centered Gaussian. Or the variance, if you wish. Okay, so we already saw this. If you take G equal one-dimensional Wt, and you take G equal 1, and you take F equal to I don't remember. Okay, it was the exercise I did yesterday at the end. So I don't remember now. I don't remember fully the exercise. And so G has to be 1, and F has to be x squared. I don't remember. Anyway, it was the exercise of yesterday. And so, but okay, this is a multivariate Gaussian, and okay, assume that the components are independent. No. Okay, assume the components are independent, so it's easier. And so you write this in terms of the density of the Gaussian. You do integration by parts in the standard way, and since there is also the Gaussian density, when you do the integration by parts, you move the derivative. Here you get two terms. One is the derivative of G, and the other one is the derivative with respect of the Gaussian density. And then you get an additional term. Now let's go back here and see what we got. And there might be a minus somewhere. Okay, and now let us compare, because here we have the derivative and the increment. So let us prove the duality formula. So we have f, which is f of some increments, and so the Mallaman derivative is the sum of the derivatives times the interval, and u is a process like uk times pk and pk plus 1 n. Okay, and if I do this product, so I take the expectation of the product of u times the Mallaman derivative of f. This is simply okay. all these intervals are disjoint, so when I do the product, it's simply the product of all these terms. So this is the sum of the expectation of uk derivative of f over h d and k, and these functions are computed on the increments. Okay, so if we look at the remark, and what is our g? G is the random variable, the random vector which gives the increments. Okay, so here we have so u and the derivative of f, and so we integrate by parts in this way, and this is okay. So u is g and f is f, so that's easy. So now we can compute this. This is f of the increments times uk times the increments, but it depends on each increment, on each time increment, and so d and k over 2 to the n, because each increment is an increment over a time span of 1 over 2 to the n, and so the variance of the increment is 1 over 2 to the n minus the derivative of uk over d and k. Okay, and if I did everything correct, I should get the same formula, which I didn't because I got 2 to the n there. Sorry? Oh, yeah. There must be an error, but because I didn't take into account something. I didn't take into account the amplitude of the interval. Okay, so this is 1 over 2 to the n, and this is the inverse. Okay, so this is times 2 to the n, times 2 to the n, but there is 1 over 2 to the n in front of it, and then I get the right one. Okay, fine, sorry. This is the inverse of the variance. So since the variance is 1 over 2 to the n, the inverse is 2 to the n. But there is 1 over 2 to the n because I consider the size of this because I'm integrating in 0, 1, and so I get the right one. Okay, so cool. Another reason why the spherical integral is defined in that way is that we have to take into account that we are integrating by parts with respect to some Gaussian random variables. And so there is a density which is not the flat density of Lebesgue measure, 1, but it's a density which depends on some function. So when we integrate by parts, we get an extra term. Okay. Now, so the duality formula is useful because first it gives us, we won't explore this because it makes the whole thing complicated, but let us give the idea. Okay, let us define a norm on simple functional. So for a functional f, we define the D12 norm. So this is a kind of, so this, now the scheme is exactly the same that you get the weak derivative in H1, for instance, as you define the derivative of C infinity functionals, and then you take the closure with respect to the norm of H1. So we define a norm, and this square is the expectation of f squared plus the expectation, okay, even better, plus the expectation on the integral 0, 1 because we are working in 0, 1. And then if we are working with a larger time horizon, we can consider the different one. Malemán derivative times Malemán derivative itself in L2, 0, 1. Okay, I wrote in this way. Okay, and this is an honest norm. Well, okay, and clearly and the space of simple functional is not closed for this norm, so we can take the closure the simple functional in L2 omega for the norm. Okay, if you're familiar with the space H1 obtained as a closure of C infinity in L2 for the H1 norm, this is exactly the same. And so this we call this closure D12. And so this is our space of functional which have one Malavant derivative. And okay, that's fine. And now, as in the same way as we obtain D12, then we can obtain D1p, where we do the closure in LP, because again, these simple functional are in L2, but we are integrating against a Gaussian kernel. So we can integrate any polynomial. So if we take, rather than the second power, we take the p power, we still have something which is finite. So actually, these simple functionals are also in LP for any p. So S infinity is contained in LP d omega, and so we can consider D1p has the closure of S infinity in LP for the norm D1 in which we have p power here, right? I mean, okay, here we have already a square, so we take the p over 2 power, so that the homogeneity is the same. Okay, so it's homogeneous of order p. I mean, otherwise we are doing something wrong. And okay, now I don't want to go into details here. I leave this at your imagination. We got one derivative. We can go forward and get more and more derivatives. How does it work? Because we define a derivative for a simple functional, and we obtain the process. But if we do one derivative, we obtain a process. And how to do the derivative with respect to a process? Well, since this process, at least for simple functional, has coefficients, each of them is a simple functional. When we do the second derivative, we are doing the Malavant derivative of the coefficients of the process. Okay? Now, I'm going to make him confuse again. Here we did the derivative, there was one time. When we do a second derivative, we have 2 times, right? Because we are perturbing in 2 different ways. So when we do the second derivative, for instance, we have S1, S2, and we're doing the derivative with respect to the first time, and we get a process, and then we do a derivative of each of the coefficients, and we get the second for the second time, okay? And etc. I mean, I don't write the formula. And then this allows us to construct the KP. Same idea. I mean, I'm not going to use all these, so I don't give full details, but it's reasonable that we can, once we have a derivative, we cannot help ourselves but doing another derivative. I mean, there's no way. And so we can do any derivative as we can, as long as the functional is smooth. And then for this process, we do the closure in the corresponding for the corresponding norms, and we get a space. Okay, so I repeat the idea. We want to differentiate with respect to the driving linear process, or if you wish, we want to differentiate with respect to the noise, because if we differentiate with respect to the increments of the quantity, and then we allow by taking more and more dyadic points, we are differentiating with respect to smaller and smaller increments. And so in a way, we are differentiating with respect to the noise, because once this interval was smaller and smaller, up to the fact that we should divide by the right sides, we get the derivative of the linear process. And so we are differentiating with respect to the noise. And that's why it's interesting to start with increments. Because in the end, what we are doing is we are differentiating with respect to the increments of with respect to the noise. Okay? Time is... Okay. Now we introduce all what we need. Now we have one important properties, which is chain rule. The good news is chain rule holds. And this is works this way. F is D12. Phi is say infinity if you wish, but then by approximation we can manage to have even a C1 function with polynomial growth. R. And so if we do the Mallaman derivative of phi of f, this is phi prime of f times the Mallaman derivative of f. And that's a good thing, because chain rule is always useful. So what the formula says, that if we start with the random variable in D12, and we take a C1 function, and we compose the function with the random variable, we still are in the same class. Okay? So again, phi of f is in D12, and its derivative is this one. Okay, I also made a proof of this, but since we already seen this, it's fine. So what the idea? How do you prove this? Well, same way as you would do in H1 if you want to prove some inequality. So what you do? You find some approximation of the functional. Which kind of approximation? Well, approximation in terms of simple functional. Then you compute and you prove this formula on simple functional. It's obvious that this is also a simple functional, because to be a simple functional, it should be C infinity. So that, but okay, let's say C infinity, and then we go to we approximate also in phi, and it's fine. So we prove this on simple functionals, and is a one-line proof. I mean, as I prepared, and then we go to the limit, and we get it for all functional in D12. Okay, so we got the two important formula, the duality relation and the chain rule, and we're going to use the chain rule. And the second thing we need is the so-called Mallaman covariance matrix. Okay, so assume f is a d-dimensional random variable. And okay, how do we define the derivative of a d-dimensional variable? Well, it's the derivative of each component. I mean, and then we can compute. Okay, we compute the derivative as okay, and then we define the Mallaman matrix. Define this has the product of the f I d f j, and this is again the product in L201 because we are working in L201. Okay, why the Mallaman covariance matrix is so interesting? At least for our purposes. For our purposes, is extremely interesting. And I want to give you an example that shows that actually this is the case. So let us do a couple of examples, because right now I give you one definition after the others. You are completely stoned. Now let us stop and give a couple of examples. So the first is the following. Say, no, we change the name. Say B is a d-dimensional Brownian motion. Oh, no, sorry. No, let's use the same letter by the underlying linear process, because it's funny. So W is d-dimensional linear process, so we define the derivative starting by this process. And say Q is a d by t matrix, and I consider as function this one, QWT. Okay? Q is d by d, W is a d vector, so F is again a vector of size d. How we do the derivative of this? Well, it's extremely easy because this is a simple functional, essentially. Okay, I don't need to fix a time. I say I fix time 1, for instance. And so this is essentially a simple functional, actually a simple functional of order 0 or 1. 0, of order 0, so the simplest one. So when we do the one-to-one derivative of each component, this is simply the sum of I'm not sure I put them. Okay, yeah. I'm not satisfied. Wait. I don't make the derivative. I said it's extremely simple, right? And I'm stuck, but it's simple. I mean, okay. So this Q, let me do is so Fi is equal to the sum of W R I. Okay. Okay, let's do it this way. I give you the result and then I think about that. Because then once we do this, we compute the Malavan matrix. And Ij. And this is essentially the sum equal to 1 to d of sigma ER, sigma JR. So this is the result because this is what I want to go. And then let me think about that. I mean, I don't want to waste all my time because I'm not figuring out this simple thing. And so this is essentially sigma star Ij. And the result is, so I know what is the result, that's why, that MF is sigma, no. Okay. Q is sigma Ij. Okay. And so the result is, so this is Q. And the result is that this is the covariance of QW1. Okay, so that's why we call this covariance, because it's in the simple case of Gaussian random variables, this is exactly a covariance matrix. And an important observation is that, well, I didn't say anything about this matrix. Okay, it has to be a covariance. So, Q star is symmetric positive, and assume that Q is of rank smaller than D. Okay? So if Q is on rank smaller than D, then this random variable F cannot have a density with respect to the Lebesgue measure in RD, because it's concentrated in a small space. I mean, there are some. But if we go and look at the Malemán covariance matrix, which is the same, also the Malemán covariance matrix is degenerate. Vice versa, if, actually, only if, this is of maximal rank, then, okay, this has a density, and this is invertible. Okay, this is a very simple example, but we will see that this is the crucial point. That is that if the Malemán covariance matrix is invertible, then we can find a density. This is a very simple example in which, well, very simple up to stupid details. But it tells us that the invertibility of the covariance matrix is equivalent, in a way, is equivalent to the existence of a density. Why I mean is in a way, because, well, the Malemán covariance matrix, the way we define it, is a random variable. And so we have to understand what do we mean by invertibility. It might be invertible almost surely. It might have some moments, and so on. Okay. So depending on the properties of invertibility of the Malemán covariance matrix, we will see that we will have stronger or weaker conclusion on the density. Okay. I have a second example and an interpretation. Now, I was trying to tell you the fact that the Malemán covariance matrix is, that the Malemán derivative is a derivative along the noise. Now I want to give a different interpretation that in a way shows you exactly this. If we do the calculus of variation on the driving process, we get the Malemán derivative. And in fact, Malemán himself called this the stochastic calculus of variation. Okay. Well, he didn't call Malemán calculus. It's not something you do. But he called it stochastic calculus of variation. There are different versions of the stochastic calculus variation due to Struck, Bismuth, and Malemán itself. And the version I presented here comes, as I told you yesterday, comes from some notes of Vlad Valley. He is in Paris. Okay, which is the example. Say, now it's a bit more complicated. Say f is integral from 0 to 1 of h of s times dWs, where h is in Rd, and w is d-dimensional linear process. Okay. And okay, so now let's look at this. This is Ito integral. So we can approximate this in terms of a simple functional. How? This is the sum of h at some sample at some point, for instance, the dyadic point, times the increments, right? And this is essentially how you get the Ito integral, the differential Ito integral. You write this, and then you take the limit over all this time sampling. So, I mean, the derivative, the Malemán derivative here is essentially h of s. Okay? Because an approximation would be something like h, s, and k, delta, and k. And then the derivative would be exactly this, and then so on. Okay. Then, okay. This is the derivative, and if we compute then we can also compute the matrix. Ij is equal to this is simply integral from 0 to 1 HIS HJS. Okay? And so this is another example in which we compute the derivative and the matrix. Now let us go to the interpretation in terms of calculus of variation. And we use this example. Okay. Let's take f equal to integral of h dw. Okay, so you see that this functional is a function of the path. Okay, and then there is also h, but h is part of the manipulation we do on the path. Okay, so we can see f as a functional of the path. Okay, because we obtain this as, in terms of this, a limit of this. So the manipulation we do on the path are sample, multiply by h at sample point, take the limit. Okay, and this is our functional phi. Okay, so now a derivative is we perturb the independent variable and we get a perturbation of the dependent variable. Okay, so we perturb this and we get a perturbation of this. Okay, okay, so which kind of perturbation we should consider? Again, we go back to our lectures and we know that if we go and perturb a Gaussian measure, we should do it in the right direction. So the direction of the Cameron-Martin space. So this is a Gaussian measure on the space continuous function on 0, 1. And so there is a precise definition of what is the Cameron-Martin space in this case. And the Cameron-Martin space is the space H1, essentially. H1 of 0, 1. So this is a process in a continuous function in 0, 1, and the Cameron-Martin space is H1 of 0, 1. Okay, so our perturbation will be perturbation in the Cameron-Martin space. So we want to perturb this, so we take epsilon, and we take a perturbation, and since it has to be a perturbation in H1, which is going to be, so it's going to be some kind of integral of a function in H1, so something in L2. Okay, so we get a new noise, so to say, that comes from this process. So W epsilon t is Wt plus epsilon 0t ds, where V is in H1 of 0, 1, which is the Cameron-Martin space of C0. I didn't tell about this, but now we know what is the Cameron-Martin space. I won't go into details of why the Cameron-Martin space of C01 is H1, but we know what is the Cameron-Martin space, and we know why we have to take variation along the direction of the Cameron-Martin space. That's what is important. So this is the new noise, and then we can define a new random variable f epsilon, which is same functional, but on W epsilon. So to say, okay, here what we do some integration and some limit, but since we are perturbing with something with respect to which we can integrate, because this is a bounded variation, okay, so we are fine. We can, the manipulation we do on the path can be done also in this way. And that's a good reason why we should do a variation along this direction, because the manipulation we do makes sense. But the real reason is these are the direction of the Cameron-Martin space. Okay, and so what we do, we consider f epsilon minus f over epsilon, and this is a derivative, which is essentially this one. But wait, we know f because it is explicit, so we can plug who is f here and who is f epsilon, because this is the same manipulation but on this process. So this one is the integral of h dw plus epsilon integral hv minus the integral h dw over epsilon. And I took too much space. If we do all the computation, we end up with I rewrite here, f epsilon minus f over epsilon. We end up with integral 0,1 of h v ds, which is very disappointing because this is not the Maillard derivative. It's true. And it has to be not this one. Why? Because as we know, we are doing a derivative along a direction. So we cannot expect to have the Maillard derivative. We expect to have a directional derivative. Okay? So that means the product between the Maillard derivative and the direction in the scalar product in the space where these things live. So this is the scalar product between the derivative and the direction. That is the FV. Okay, now this makes sense because that's what we would expect. We do a direction derivative and we get the product between, say, the gradient and the direction. So nothing else than what we would expect in a standard case. Fine with this? And so doing Maillard derivative is essentially doing calculus of variation on the noise. Okay, I'm almost, very almost, 10 minutes. But I have only two things to do. So I should stay into the 10 minutes, maybe 12. Okay. We go back to this interpretation because this will provide us a very quick way to compute the Maillard derivative when we are dealing with a stochastic differential equation. And I will close with showing that if we, as a stochastic differential equation on an infinite dimensional space, we take our favorite model, so the Navier-Stokes equation, the Maillard derivative is, well, I wouldn't say is not differentiable because we don't know, but if ever, we will see that if ever we can prove something on the Maillard derivative of a solution of a Navier-Stokes equation in 3D, we are extremely in business to do much better. That is worth $1 million. So you see, it's out of our possibilities. Okay, so the first thing I want to do is finally the integration by part. So that FG in, we need, let's say we took in the smoothest situation, so the infinity, which means this is the intersection of D, K, P for any K and every P. So these are, it's like C infinity in the standard setting. And we have one integration by parts. And for higher integration by parts, you do the same. But okay, so you have the gradient of phi in F times G. This is equal to the expectation of phi of F. Fair enough, because this is what we want from the integration by parts, and we need the weight from the definition of integration by parts. And this weight is given by G times the Maillard derivative inverse, and F. So this is the scalar integral of this term. So the weight that we need to get an integration by parts is given by the scalar integral of the inverse of the Maillard derivative. Okay, so now this tells really that we need to have a good Maillard derivative to have an integration by parts and so a density. So how to prove this is very quick. We have all we need to do this. Okay, so first we compute the Maillard derivative of phi of F, and this is chain rule. This time is multidimensional, but if it holds in one dimension, it holds in any dimension. This is the gradient of F times the Maillard derivative of F. Okay. Okay, so if we multiply these by the Mallaman derivative, so what we get is times the Mallaman derivatives of f. This is equal to gradient of phi of f times derivative df, Mallaman derivative df. Okay, so why we do this? Because if we do the product of Mallaman derivative df with itself, we get the Mallaman matrix. Okay, and why we get Mallaman matrix? Because we want to write the usual gradient as a gradient in the sense of Mallaman. Because we know how to integrate by parts with Mallaman derivative, and we don't know how to integrate by parts with the standard derivative. Okay, so we transform the standard derivative into Mallaman derivative, and we pay a price. And this price is the fact that there is the Mallaman matrix. And so what we get is that the gradient of f is equal to this product times the Mallaman derivative minus 1. Okay. So, if we write this, and we replace, this is the expectation of so g, and then there is Mallaman derivative minus 1. Okay, here I should be careful with the matrices because we have matrix and vector. So this is an inverse matrix that applies to this as a because this is one dimensional, this is d dimensional, and this is d by d. So this applies to this. Okay, and so we got this, and now we use integration by parts formula for actually the duality formula, which is an integration by parts in a way between the Mallaman derivative and the Skorod integral. So we take this derivative and we move it here. And so we have phi of f, delta of g, and f minus 1. Okay. So no derivative on phi, and we have an integration by parts. So that's why Mallaman calculus provides a way to provides some ways for the integration by parts, because we can move a standard derivative in a Mallaman derivative. And while here we don't know how to do integration by parts, we would know if we knew something about the regularity of the density of f, but we can't. And in this case, on the other end, we know, well, if possible, the regularity of the Mallaman derivative. It's our assumption, after all.
So, I thought you missed a little opportunity in the site you erased. You had the Ito integral, and then you calculated the Mallaman derivative and showed that the argument integrand is in fact the Mallaman derivative, right?
Yeah, in this simple case. I mean, it's
in finance, let's say you take the Black-Scholes formula and then you go to the risk neutral, right? Then you have the martingale representation. So the hedging function H is in fact the Mallaman derivative of the price.
Yeah, because this is the Clark-Ocon formula.
Right. So that's a nice example.
Yeah, you're right. But I'm not really into the finance, so I always miss the opportunity to hook them with finance. Okay, so good thing. Now the last part is in our last 2 plus 3 minutes. That I mean that I hope the organizer will give me the last 3 minutes. Let us see what happens to SD. So let's take an SD. Dx is equal to b of x dt plus sigma of x dw, and we want to see if we can compute the Mallaman derivative of the solution of this. Why? Because if we want to show that there is a density for a solution of a stochastic equation, so what we do, we use this integration by parts. So we know that if we have the Mallaman derivative, if we can prove, well, we need much less than this. This is a really lazy man theorem. which we make safe bet that our assumption will be contained here. So we are proving a theorem on C infinity of something which only needs one derivative. So definitely we can do much less than this. And so we want to compute the Maillard derivative of this. So what we do it in a very heuristic way, using the fact that this is a stochastic calculus of variation. So what we do a perturbation in the noise. The perturbation is in the Cameron-Martin space. So we take a perturbation, we take an epsilon, and we have our noise, W epsilon, which is W plus epsilon integral of V. And with this new one, we have another equation, which is dx epsilon equal to bx epsilon dt plus sigma x epsilon dw epsilon. And I write below the original one because I want to make the difference, divide by epsilon, take limit as epsilon goes to 0. Okay, make the difference. Dx epsilon minus x over epsilon is equal to b x epsilon minus b of x over epsilon dt plus, okay, and here we have, here there is dw, there is the dw epsilon. So we have sigma x epsilon minus sigma x over epsilon times dw plus, there is the last term, sigma x epsilon times v dt. Let us take the limit. Now, okay, this is all heuristic, but it gives the right answer. So this is the Maillard derivative of x. Chain rule. This is, let's say, we are in one dimension. This is the derivative of b times the Maillard derivative of x. A chain rule. Also here. And x epsilon goes to x when epsilon goes to 0. Okay. And so what we, we got an equation for the Maillard derivative of x. That means that if x is a solution of this SD, if the coefficients are regular enough, then the solution is Maillard differentiable and satisfies this equation, which is nothing less than the linearization of this equation. Because what we do the derivative of the coefficient times the solution. See? So there is nothing less but the linearization. Okay, and then there is an additional term that takes into account that we are doing a variation along some direction. So now, let's say, can I speak for 2 minutes more? Do you mind? You do mind, you mean? So if you do this on Navier-Stokes, so let's go back to our finally for today, which you notice that I never said the word Navier-Stokes for today, but now it's time to do it. And our model is du equal plus au plus d of u. I want to emphasize that this is quadratic, so I put it here. And this is some noise with some covariance that I don't make it explicit. And so if we do compute the linearization, this is the derivative of u plus, okay, this is a linear, so the derivative is a of du plus, this is quadratic, so the derivative of x squared is 2 times x, or x times, okay, this is not commutative, so we have to have this. Is equal to dw, no, not dw, because here this is 0, and we have simply, okay, let me write the covariance explicitly. Okay, now forget about this term, because that's not going to change anything. Say you want to show that there is a unique solution, right? So you have two solutions, U1, U2, say without noise. You compute the difference between these two, and you see what is the equation satisfied by this difference. So call B this difference, and you write down, and then you discover that B dot plus A B plus B of U1B plus B of B U2, maybe it's vice versa, but it doesn't matter, is equal to 0. Okay, so point is, if we want to show that anything, we want to have any bound on the Mallavan derivative, and so on the Mallavan matrix for the solution of Navier-Stokes, well, we need to say something on this equation. But anything we can say on this equation would equally apply to this one, which is getting some information on uniqueness of Navier-Stokes, which, come on, I mean, that's a much more difficult problem than showing the existence of a density. So, conclusion here is we need different methods. The method with Mallavan derivative may work, but it's a lot of work. You find it in chapter 3, and you see that the result in the end is qualitative. You only get existence of a density, which is disappointing because Mallavan derivative is not only, the method we use in Mallavan calculus is not only that. Mallavan calculus goes through regularity of the density. We use, as a first method, we use Gilsonov formula that only gave us a qualitative result, which was fine. We would not expect anything more than that. But with Mallavan calculus, we would expect regularity, because that's the way it is. Mallavan calculus was conceived as a probabilistic proof of Ormander's sum of squares theorem that says that if you have an hypoelliptic operator, you still have regularity of the solution. So it's really a matter of regularity. And using Mallavan calculus and you not getting regularity is very disappointing. So you can do that, but you still have only a qualitative result. So existence of a density. And then you have to rely on different methods to show regularity of the density. And this is a field of research which is very much interesting in these days. And the people that is doing this is essentially like Vlad Bali and other people. And most of the application of these, like Sri likes to point out, are on finance. Okay.
So this linear problem is the same equation you get in control theory. Why don't you just estimate? You have the same a priori estimates as.
Yeah, you don't have an a priori estimates here.
You do.
You don't. Well, because you don't. I mean, one term disappears, the other doesn't. And if you are in dimension 3, you really don't know what to do with this.
It's 3, yeah, you don't, because it's the same continuous difference.
Oh, well, in 2 dimensions, sure, you can. In 2 dimensions, there are some beautiful works by Martin Heirer and Jonathan Mattingly that developed the Mallavan calculus in infinite dimension, and they proved a lot of things. Among these, they proved the existence of a density. Actually, the density is C-infinity. And even with the noise, which is extremely small in frequency, very much concentrated in frequency. So here I'm dealing with the 3-dimensional case, and in the 3-dimensional case, I cannot even touch this equation. I mean,
that's connected to the unique solvability.
Yeah, exactly. You get something out of this equation. I mean, you're fine. I mean, no, not really. I mean, no. I'm saying that getting any estimate on the Mallavan derivative is as difficult as getting any estimate on this equation. But getting estimates on this equation would give you an information on uniqueness. Okay? So I'm saying that this is extremely difficult, and the way we did to get some bounds here is to work on short times. Because this is a parabolic equation with a dissipative equation. So for a short time, there is a good solution. Yeah. So it's a stopping time, and you have almost no control on this stopping time, and so you really have to work a bit. But that's what I wanted to do today. But no way. Okay. I think I will stop here. Thank you very much for having me at the end. And traditionally, as the last person speaking, I take the occasion to thank the organizer for this nice meeting. The only thing I'm really regretting is that I could only come on 1 week. I'm really sorry, but you lucky you were me for 3 weeks, and I hope you enjoyed as much as I enjoyed this week. So thank you very much. Clap. Thanks are to you, you're the organizer. So thank you very much indeed. And thank you to all to listen to our stuff.
ఫోన్ చేస్తే ఏడా వల్లిగాడు ఉన్నాడు అంటే రాలేదని వాడు డల్ అయ్యి ఊరికి నాలుగు
If you
yeah, so
yes. Okay, so what you ask?
Yeah.
Okay.
Proof I don't see there are much derivatives on G.
Okay, so there is one announcement. We will give the certificate for participation in the school. And I will request the secretary to come here and we'll announce the names and you can come to the stage and we will distribute.
Apparently there is a Professor Navier also. Why don't you also come? So apparently there are some typos in the certificate, so you have to give the certificate back on your way out. Is that right? Something like that. But before that, I also would like to take the opportunity to thank Professor Utpal Manna and Professor Thital and the what is the organization that funded it? Yes. National Center for Theoretical Sciences. Professor Adimanti sits on the board or something like that. So thanks to him for supporting this one. Okay, so students are going to come here and we are going to give certificates. You can stand if you like.
No, I am answering the question. So if you don't mind, I will stay on the break.
Okay. Yeah, you can sit.
PM Patil.
Thank you, sir. Congratulations and thank you for your participation.
Okay, so actually, so why you need
Hasina A.
Actually, you can just get rid of this G. And there is a theorem by Hirsch.
Pooja Agarwal. Read the names.
It says that
You are from here.
B1P. If
Dharani S.
this is showed,
Dharani S is from
then this says that there is a test. This, as far as I know, is the weakest condition. And this is what we expect. Okay, this is less obvious than it will be. The real problem here is to estimate the score difference. So then you would expect that to estimate the score difference, this will depend only on you.
Suvindra M.
But unfortunately, this is not true. If you estimate this, you get
Rubel Marian Lindsay.
depends on you and on the Malavan derivative. It's very disappointing because this is an integer. You would expect this to depend on you. It only happens when you. In the general case, this show up. And so, even though here you don't have derivatives,
Yeah.
you need.
Guys, sit down. After the award ceremony, we talk.
Oh, sorry.
I know it's very enthusiastic. Yeah,
I was
it's okay.
making noise.
No. Debanjana Mitra. How do you spell it? Say it. Debanjana. Debanjana Mitra.
Yes, says it here.
She's in here for
Yes, one that.
Nishanti D.